The lower Neckar River near Ilvesheim, a small town in the southern German state of Baden-Württemberg. The settlement is enclosed by an oxbow, which is no longer used by ships, and the water is allowed to shape its bed mostly free of anthropogenic influences. This resulted in the formation of a gravel bar. Since 2011, the gravel bar has been investigated by geography students from nearby Heidelberg University. Every summer, they perform a topographical survey in order to learn about the erosion and deposition processes that continuously change the gravel bar's shape and volume. Their most important tool, an expensive piece of 21st century technology called a laser scanner. In modern geography, laser scanners are widely used to produce highly detailed 3D models of practically anything from the size of a small boulder up to entire landscapes. As the name suggests, laser scanners work by sending out pulses of infrared laser light. Whenever the light hits a surface, a portion is reflected back to the scanner, and the scanner measures the time it took for the light to travel to the obstacle and back. Knowing the speed of light, it can then compute the distance to the reflective object with very high precision. By repeating this process for all directions in lots of very narrow angle steps, the laser scanner can measure the exact shapes and positions of all surrounding objects. The result is a so-called point cloud, a dataset which contains millions of 3D coordinates that represent the shapes of the detected surfaces. The laser scanner does not only detect the geometry of surrounding objects, but also their colors, using a digital camera that is mounted on its top. In order to acquire a complete model of the region of interest, without missing parts and in good resolution everywhere, it is not sufficient to perform only a single scan. Just like the human eye, the scanner's optical sensor cannot see through objects. To capture a part of the scenery, it needs to be in line of sight from the scanner's position. Each obstacle in the field of view will produce a so-called scan shadow in the resulting dataset, an area void of any recorded points. To fill the scan shadows, multiple scans from different positions are made, so that each part of the scenery is visible from at least one position. The data which is acquired during each scan is transferred to a laptop computer, which is connected to the scanner. The computer is used both to control the scanner and to perform post-processing and analysis of the acquired data. This includes the merging of data from different scanning positions to produce a shadowless point cloud for the entire region. The computer can do this mostly automatically, but it needs some hints. These are provided in the form of special reflectors, which are placed in the surrounding area prior to scanning. When a laser pulse hits a reflector, an especially large portion of the light is returned to the scanner and a very strong reflection is recorded for the reflector's location. The scanner's software is able to recognize the same reflector in different overlapping pieces of the dataset and uses this information to put the pieces together. The registered dataset is used as the basis to answer a number of scientific questions.
Ja, ich bin von der DTM-Gruppe. Die DTM-Gruppe befasst sich mit der Punktfolgerung und generiert daraus ein digitales...
The first step is to take the point cloud and derive a digital elevation model. To verify the correctness of our model, we use alternative techniques to take additional measurements at a number of reference points spread over the entire gravel bar and especially here at the riverbank. The elevation model is derived from the point cloud by applying an erosion filter algorithm. It removes things like these shrubs and other vegetation, and we get a shape that represents the ground surface.
So Büsche und Vegetation weg, bestmöglichst. Und was rauskommen sollte, ist einfach nur ein Oberflächenmodell.
Als Methodenvergleichsgruppe haben wir dann auch noch die Aufgabe.
We test and compare different methods to measure the roughness of the ground surface, which is required for hydraulic modeling. Our first method to acquire surface roughness values is to extract them from the laser scan point cloud. The second method is called photogrammetry or structure from motion, where a computer program reconstructs the 3D shapes of objects using multiple photos from different perspectives. Additionally, we experiment with another 3D scanning technology in this little tent behind us. Inside, we try to capture the geometry of a small patch of ground using a Microsoft Kinect stereo camera sensor. The tent is required because the Kinect sensor doesn't work correctly when exposed to direct sunlight. Finally, we will also estimate the surface roughness in a very traditional way, that is, by manually measuring the size of a few randomly sampled pebbles.
Die Oberfläche in ihrer Gesamtheit aufzunehmen, weil das Tageslicht störend auf die Messung einwirkt.
Also meine Gruppe macht eine multitemporale Analyse. Das heißt,
We are conducting a multitemporal analysis with laser scan data from 2011 and 2012. We are going to use the 2013 scan as well. In addition, we are measuring several of these metal rods by hand. They were driven in to the level of the gravel bar last year, and this one is now protruding by 56 centimeters.
Zentimeter raussteht. Unsere Gruppe erstellt mit Hilfe von
Our group will use the digital terrain model to perform a flood simulation. There was a flood on the 3rd of June 2013 up to the level of the path on the other riverbank.
Radweg.
We are going to compare our model with different digital terrain models that vary in resolution.
Kleineren Auflösung vergleichen.